This is part 3 of the rates and equilibrium topic. It's GCSE AQA chemistry and it's for dual and triple award students. I'm going to recommend you have a go at each activity, pausing as you go. So in this particular video, we're going to focus on the effect of temperature on rate of reaction, and we're going to revisit collision theory that we looked at in the previous video. So, recall the impact of changing temperature on rate of reaction and use collision theory to explain the impact. So have a think about these questions and then we can review them. So do we think that increasing temperature will lead to an increase or decrease in the rate of reaction? And I hope that most people watching this video are recognising that at higher temperatures things tend to happen faster. We know that when we cook at higher temperatures things cook faster, for example. So increasing temperature will increase the rate of reaction. And in terms of current level of understanding of collision theory, it depends if you're revising or looking at this at the start of learning the topic, but we are going to build an idea here and develop it later in the video. We would potentially expect that higher temperature means a higher energy, and that therefore means there are more collisions. And if there are more collisions, there are more successful collisions. And we looked at a very similar idea with surface area. In surface area, when we broke something down into smaller pieces, we found there was greater surface exposed, so there were more collisions, so there were more successful collisions, so the rate was faster. As we go through this video, we're going to find it slightly more complicated with temperature. So we have here a couple of questions, something for you to read, and a good example of using a model to remember something that's perhaps quite abstract. So in this model, we have an irresponsible teacher setting up an experiment in the classroom. Move all of the furniture out of the room, ask the pupils to walk in, close their eyes and walk around the room. Once they've done this for a short time, the teacher asks them to run around the room, still with their eyes closed. What do we think would be the difference in how many times people bump into each other when they're walking compared to when they're running? And there's a common sense here that you would expect people to bump into each other more often if they're running rather than walking. That helps explain more collisions. We can imagine that as particles moving faster. Now let's think about the intensity of the impact when they walk or they run. What would the significant differences be? Well, we've already established that they'll bump into each other more often. But they're also going to bump into each other harder. They're going to bump into each other with greater intensity. And in this model, that might mean that the collision results in a reaction. That reaction might be an injury. They might be knocked to the ground. They might injure their ankle. So in this model, an injury is a reaction. Now let's take a look at that model and try to apply it to collision theory. Why does changing temperature have an impact on the rate of reaction? There are two factors at play here, and this is what makes temperature different to the other factors that we consider. Those two factors. One, there is a greater frequency of collisions. And if there is a greater frequency of collisions, just like in all of the others, there'll be a greater frequency of more successful collisions, more collisions that result in a reaction. But in addition to this, there's a higher proportion of these collisions that will have an energy equal to or greater than the activation energy. So if I double the number of collisions and a greater proportion of those collisions result in a reaction, we can see why increasing temperature has quite a significant impact on the rate of reaction. And in all of the other examples that we look at, we generally consider that doubling pressure, doubling surface area, doubling concentration will double the rate of reaction. In temperature, we generally find that for every 10 degrees Celsius that we increase, the rate doubles. That's a much bigger increase, and the two reasons here explain why. So let's have a look at a practical that helps you to see this. The disappearing cross experiment where sodium thiosulfate, we can see that sulfur is made, which is a yellow solid. It causes the liquid to go cloudy, and we can no longer see the cross through the top of the conical flask. And in this, we time how long it takes to see when the cross disappears. Now, it says here the equation needs balancing, so it's a good opportunity to practice that. And I can see straight away I've got two NAs, I've got one NA, so let's balance that one. I've now got two CLs, so I'll need two HCl on the left. I've also balanced my H's as we go. So in terms of the method, it is really important that you are familiar with the process of this. You can see here we're doing it at different temperatures. And as I've already touched on though, we are reacting the sodium thiosulfate with hydrochloric acid and timing how long it takes until you can no longer observe the cross on the piece of paper through it. But I do recommend you just pause, have a go at this, or even try to write this down and come back and review it. How successfully can you replicate this method? In terms of the results table, this is a good example. I've spoken on previous videos about having a place to show the independent variable. In this case, it's the temperature, the thing we're changing, and we show the dependent variable, and that's the thing we measure as a result of the change. I've included units because they must be included where appropriate, and you can see here we're actually doing each experiment 3 times and calculating an average. Now I've put some data in here, and the first thing to do before you calculate the average is decide, is there any of this data that we would not use? Are there any anomalies? And if I take a look through here, I can see 60, 58, 62 are all quite similar. But 56, 48, 56, 48 definitely stands out as being far away from the other two. As a general rule, if one of the numbers is more than 10% away from the others, you wouldn't include it. So 10% of 56 is 5.6, takes you down to just over 50. 48 stands away from that, so we disregard it. And if you go through the rest of the table, and you can see which others you would disregard, and the only other one that really would be disregarded here is 24. The others are within the range. 30, 10% is 3, so down to 27, up to 33, that works. 12, 12, 12, all identical. Once you've identified anomalies, it is then possible to work out the average. And remember, you don't include the anomaly in the average. And then from there, if you want to have a go at this, you can get some graph paper and try it, but you need to plot the graph. And on the graph, the first thing to talk about is that you are going to label the axes. And again, we've got here the independent and the dependent variable. And I've included the units. And then I need to add my scale. Now, on here, there's not a huge amount of space, but on here, you can see suitable scale. I have used more than half of the available space. From there, I'm going to plot the points, and there can be marks available for plotting, so do that with care, because you don't want to lose what can be quite straightforward marks. And I've got those, and then I need to do the line of best fit. And you can see, we're not going to just join these points up. There are some anomalies within this. I need to show it's a curve, so I'm going to show the best curve I can that represents the overall trend. And I've done that here. So from there, let's have a look. What is the trend shown by the data? Well, we know that increase in temperature increases the rate of reaction. We actually know that because the time taken for the reaction to take place has decreased. And explaining using collision theory, well, 2 factors here for temperature once again. There is a greater frequency of collisions, and a greater proportion of particles have energy equal to or greater than the activation energy, which means a greater proportion of those collisions are successful. Now we've got a question here predicting what the temperature would be at 60 degrees and 25. Well, let's take a look. If I go to 60, I can go up, I can read across, and it comes to 5 seconds. But if I go to 25 degrees C, you can now see a major problem with the scale that I chose. And we need to be considerate of this when we are plotting graphs and when we're choosing scales. Because if I were to go down to 25, it actually sits off the scale. I can't possibly read that. Now, in an exam, that might mean I've got to go back and redo the scale. It certainly would be a difficulty. So it's why it's important to read through the whole question and decide on the scale once you've considered what you're going to have to do with the graph afterwards. So on this one, it's not readable. Scale on graphs, hugely important. Okay, some more questions. Why did we repeat measurements in the experiment? And first of all, we're testing the repeatability of the experiment. Remember, repeatability is whether you can do the same thing again and again and get similar results. Reproducibility is if somebody else can do it or follow a different method and still get to the same results. Remember, to reproduce, you need more than one person. So repeatability is you doing it. Reproducibility is other people doing it and still getting the same results. But the key to this is we're identifying and discarding the anomalies. Now, it says here, include examples of results. We actually spoke about those in detail earlier within this video. So it could be difficult to judge when the cross has disappeared. You're basing it entirely on your own vision. And it might just be that you're not confident that the cross has fully disappeared. You might go too early. You might go too late. How could that be improved? Well, a really common way is to use a light sensor. You shine a beam of light through, and the sensor on the other side, we time how long it takes until the light no longer reaches the sensor. It's a much more automated approach. We're taking away that human error difficulty that we might otherwise face. Okay, as an alternative practical, students timed how long it took for a tablet to stop fizzing when added to a fixed volume of water. We've got a table here, and you can see there's a column, and the first question on here is calculate the mean rate of reaction. So how would you do that? Have a think about it. And essentially, we know that we have got 3.5 grams, because that's the size of the tablet. We divide that by the number of seconds it takes to fully dissolve, and we find that we have got these figures, and we can see the mean rate of reaction increasing as the temperature goes up. From there, how could the accuracy be improved? Well, maybe we could actually measure the volume of a gas. We could use a gas cylinder and measure over time how much gas was being produced as the effervescence continued. Some more questions. Describe the impact of increasing temperature and explain it using collision theory. Already talked about this, but it's good reinforcement. Can you remember from earlier in the video? Increasing temperature increases the rate of reaction. Remember, it's actually around 10 degrees Celsius will lead to a doubling in rate. An explanation using collision theory. Particles are moving faster, greater kinetic energy. So there's a greater frequency of collisions, and a greater proportion of particles have energy equal to or greater than the activation energy, which means a greater proportion of collisions will result in a reaction. And to finish off, what could we do if we wanted to amend this same reaction to measure the impact of surface area? First thing is we make sure we carry these out at the same temperature now. That becomes a control variable. But then we do exactly the same as we did, but we might crush the tablets up into a powder. We might halve the tablets. We might quarter the tablets and investigate in each case how long it takes for the fizzing to stop. At that point, we are investigating surface area. So that takes us to the end of this video. Thank you for listening, and goodbye.